Thank you. All right, so let's talk some machine learning. Before I start, I just wanted to gauge the level here. So if you could please raise your hand if you know what a convolutional neural network is. Okay, so a few. And could you please raise your hand if you know what cross entropy is? Okay, excellent. Okay, so the state of machine learning 2018 themes at ICML. Why is it called like this? So one of the reasons is that Johan that booked me into this meeting, he said you can have a maximum of 50 characters. So of course I picked exactly 50 characters. So that's one of the reasons. And when I was trying this character counter out, I saw this one up here. So it says my readability level. And I thought it was pretty interesting because it could be machine learning. It might not be, but like a lot of stuff is machine learning today. So I thought, yeah, it probably is interesting. Let's try it out. So I tried it out a little bit. So this is a sentence from French philosopher Derrida. He's famous for this like a strange, very hard to understand language where you, if you start when you're finishing a sentence, you kind of forgot what it started with. So and it actually says college graduate. So it's yeah, so far so good. Then I tried out one of these. So this is of course a Trump tweet, and it's 7th to 8th grade. It's so yeah, it seems pretty good. And perhaps I should say also that this doesn't have to be a critique of Donald Trump because it's well known that he has this type of speak, and it could be because he wants to reach a larger audience. So who knows? But yeah, it's spot on so far. But then I thinking perhaps I should stress test it. So I just write one letter and it says college graduate. So obviously when they trained this one, they didn't have a class that was a no class, null class, you know, like I don't know. So it has to choose something. So it choose college graduate. So yeah, they should probably retrain it a little bit. But yeah, pretty good. All right, so back to ICML. So ICML is a conference. It's academic conference, so one of the highest rated in the world. And this year it was in Stockholm, so I was very lucky. Usually they move around a lot, like different capitals. So good to have it in our backyard this year. Since it is a academic conference, there was a lot of grad student there, and they have this like very specific and deep talks. So I was thinking that instead of me picking like the 3 talks I like the most and deep dive into that, because this was like 3 days and the talks were 15 minutes each, something like that. So I was thinking instead of picking specific talks, I will talk about the themes, you know, the overarching trends in machine learning this year. So so basically what I will do, I won't go into details. I will more or less spit a bunch of buzzwords at you for like 45 minutes. All right, so how do I find the themes? So that is a machine learning problem in itself. So perhaps you can do some like a clustering with some word embeddings or something like that. But it's very hard because it's very technical language in the papers. So I think like the usual word embeddings wouldn't work to cluster. So instead I go with a very well like well-known method, which is word frequency. And lucky for me, they already done that at the conference. So here we see this is just like counting words from the papers that were accepted. And as you can see, deep learning, this is what it's all about. Okay, so it was like so big at the conference, deep learning. We can also see that there is some reinforcement learning up here, and also some optimization was pretty big. But yeah, deep learning, neural networks, that was like, yeah, a lot of that. And this might surprise some of you. So if you're in the industry, perhaps you're used to these, like linear regression and stuff like that. But yeah, so at this academic conference, it's not so much about what is useful in the industry. It's more what is being researched right now. So less of these and more of these. Okay, so after thinking a bit about it, I thought that the themes is obviously deep learning and reinforcement learning. And then also, when I went out to the hallway, there was this chess tournament there. So I was thinking I will say a couple of words about that. Also, fairness was kind of big, and I thought it was pretty interesting because it's more it's less technical. So I was thinking I take that one also. And the future at conferences like these, there is obviously always a bunch of people that like to speculate and think about the future. So I'll talk a little bit about that also. Okay, let's start with deep learning then. One thing that was really hot in deep learning right now is generative adversarial adversarial networks. So you've probably seen these. So these are celebrity faces, but none of these celebrities exist, and so they're generated. And I thought like this is pretty amazing because our brains they're so good at recognizing faces. You know, if you've seen computer games or some animated movies, faces are super hard because our brains are so wired to recognize small stuff that is if something is wrong, we will recognize it very fast. So and I don't know, I don't see anything wrong with this. You know, it looks like real people. So yeah, very good. Here is also generated pictures. So here's a text that describe like a bird, red bird, and stuff like that, and then the network generate birds like that. So yeah, pretty good. Here you can write, you can draw some outlines, and the network will generate a cat that looks like your outline. And here you can take some pixels, like a very pixelated image, and it generate like what the picture might look like. And I thought this was pretty fun because it has long been a joke, like in television series where like someone has written that like the director might not or screenwriter might not be a technical person, so the character says like, oh, enhance this picture and enhance it even more, and you can't really do that because you just get a more pixelated image. But yeah, perhaps like CSI is 5 years into the future and they're actually able to enhance like this. So so yeah, it's pretty interesting, like yeah, how the tables have turned. Okay, so oh, sorry. Uh, this one is real, and these are the ones that they have like pixelated or exactly, and these are the generated. Okay, yeah, yeah. Okay, so how does these things work? So the idea is pretty simple, but also genius. So you have two networks that are competing. So one network is spitting out images, and the other network is trying to find out if these are fake images. So one network make fake images, and the other one is trying to find out is this generated fake images, and then they kind of compete like that and get better and better. So one network is getting better at generating images, and the other one is more getting better at spotting fakes. And then they go on like that until there is the generator is so good that the other one can't really see a difference. And yeah, there are a couple of different types of these. So uh, like deep convolutional again, it's more of the first one, you know. Oh, yep. Oh, okay, okay. So you have real world images, and you give them, and then this one says, is it real or fake? And if it says this one is real, it gets rewarded, and this one it gets punished, sort of. Okay. So, so the first one, deep convolutional again, that would be like the celebrity image. So it just spits out a bunch of different faces. The conditional, it would be more like the cat. You know, you have a condition, which is the outlining, and Infogan. I won't go into that. Wasserstein-GAN. It so it's a little bit newer GAN. So the first GANs you didn't really know if they were converging. You had to have a human that looked at the images and says, okay, they're good enough, we can stop now. Wasserstein GAN, actually, they stop by themselves when they're good enough. So they're using another distance function. Yeah, perhaps I should say that also before I forget. So after the pizza, we will have some Q&A. And if you want to know more about some of these, you can just, just save your question, and then we can go into these more. One of the talks had one thing that really hits home with me. It was generating sprites. So not these sprites. I couldn't find his real images. So, but because well, in the olden days, I used to like to make platforming games. So, like by show of hand, how many here has ever tried to make a platforming game? So yeah, there are a few guys. So, and how many thought that like drawing sprite was the most fun part? Yeah, so one. Okay. Yeah. So graphic designer guy there. So, but yeah, I thought it was pretty boring, but it had to be done. So this was like a great application. You know, you just generate a bunch of sprites, and they look pretty similar, and everyone could draw a sword and hit you with a sword. So, yeah, really good application. All right, so moving away to something else. So here we have WaveNet. So Google was there presenting WaveNet, and this is a text-to-speech synthesizer. I kind of like listening to audiobooks, but they're expensive because you have to have a human reading a whole book. So it would be really good to, if you can have like a computer do it, and then you can have like all the books in the world as an audiobook, and that would be pretty great. So, and WaveNet has come a long way. You know, it sounds almost like a human. You know, it's very hard to hear the difference. So that was pretty good. And also one interesting thing is that they used a convolutional network instead of the usual thing that you would use, which is a recursive neural network. No, no, not a recursive. A recurrent, yeah, exactly. Recurrent neural network, which is the thing you use when you have like something that varies in time. But apparently, this is like a trend that that has started to catch on. You use convolutional networks instead, and it's not that weird because actually, like wave looks like this. This is sound. So sound is also a picture. You don't really have to vary it in time. You can also see it as a picture. So instead of showing the text to speech, I was thinking that I will show you when it generates some music instead, because I thought this was really amazing. So usually when artificial intelligence generate music, it's MIDI files. So you give them a lot of scores, like sheet music for piano, and then it kind of finds out, okay, so this is how Bach used to do it, and so I should do it the same. This one is generated from the waves, from the audio. So yeah, I thought it was pretty interesting. So I'll just play you a little bit of music. One more. Okay. I don't know about you guys, but I thought that was like pretty good. You know, it could be something that I would listen to. So like it sounds kind of like this like modernist music, Alban Berg or someone like that. So yeah. Okay. Another thing that they were talking about was AI creating AI. So today, when you want to make a new neural network architecture, usually what happens is you put some PhD student on it, and then they have to build a new architecture, and the professor is happy. But it's a time-consuming process. So AutoML from Google also does this. So they use a recurrent neural network, and they use it to make new networks. So that was pretty good also. And there are some like a lot of research in this area right now. So there are also some like evolutionary algorithms that generate new networks, and yeah, I think we need it because it's starting to become a zoo of different network architectures. All right, so just gonna check the time. Yep. People were also talking about understanding deep learning. Okay, and then you might say, but Mike, you know, we understand deep learning already. It's these different layers, and we have the first layer is the lines and the shapes, and then the second layer is the eyes, and last layer is even more like the whole face and stuff like that. And if it's facial recognition, so and that is true. We do know a little bit about how deep learning works. Uh, but what we don't know, we don't have these like exact mathematical guarantees, um, and that's a problem because like if you're going to put your life in the hands of an artificial intelligence, you would like to be able to say like this is exactly how wrong it can get. So you want to be able to give like a number exactly. So here are some things that people are asking themselves that we don't really know. So we use convex optimization usually optimization, which is like the backpropagating algorithm, like the walking walking around in the landscape, and it works pretty good, even though it shouldn't, because if you have like image recognition, that's highly non-convex, so it shouldn't really work. So why does it work? And why is there no overfitting? So like neural networks are huge, so they really should be overfitting a lot more. Role of depth. So like say you have a neural network depth 5 and it doesn't work. So if you add another another layer, depth 6, does it work then? Or do I have to add 2 layers? You know, we don't really know. And that of course is a problem. So there are some people they're trying to figure this stuff out. So just on the first one, we have a highly non-convex landscape. So here's a non-convex function, which is a saddle point. So the saddle point, like in the gradient is 0 everywhere, but it's not a minima. So we don't want to stay there. We want to go somewhere else. So why does it work? So then some people have modeled this and they say, okay, they perturbed their gradient descent a little bit. What usually happens in the real world is that you always have a bit of noise in all images, so you don't have to perturb it. It's like already pre-perturbed. And then you can analyze it as a random walk. So you have some random noise and it walks around at random, and then you can say, okay, so we have a mathematical guarantee that it won't get stuck in a saddle point. So this is a pretty nice result. All right. So yeah, one reason why we want to understand neural networks at a deeper level is because they're pretty easy to fool nowadays. And this of course is a problem. We would like this to go away, or like to know how to how to make attacks like this, how to fix them. So here is a temple, and then we just add some noise, and then all of a sudden it thinks that it's an ostrich. And yeah, that's pretty crazy. And also look that it's actually more certain that this is ostrich than it was in the beginning. So it's yeah. This of course is a problem, and it's not just like a toy example like this. So there were some guys that tried this out. So here we have ordinary stop sign, and it's actually like pretty stable algorithm, because it can see that this is a stop sign even though it's shadowed, and so this would be something that you might find in a self-driving car, you know, because it looks pretty good. But then they made an attack like this, put some some noise here, and it says love hate. So this might be something that like a human walk past it and okay, there are some kids, you know, had to put these stickers on it, no big deal. But it actually, the neural network sees speed limit 45. So this is like super dangerous because if it's a stop sign, it would just keep on going. So yeah, yeah, we don't want this. So then people have tried to fix it. So the way you generate this noise to fool the AI is that you use gradient descent, and so you try to walk down and find something that is like very close, but it's not what you want. So you find something close. Okay, so could you do something to fix so that this won't be possible? And yeah, there is something you can do. You can use like this obfuscated gradient, this is called. So this basically you add a bunch like a bunch of hills and valleys, so that it makes very hard to walk around here. But of course, then this guy he managed to crack this algorithm, so we're not safe at all. And he was like, you should always assume that the attacker read the same paper that you do, and he will read your paper. So if you have this idea, oh yeah, I fixed it with this gradient, and then you publish the paper, the attacker will read that paper, and then he will try to figure out how to fix it, or like overcome. Okay, yeah. Hmm? Yeah. This is changing the neural network. So you can't find the so when you try to find this one, you won't find it. So that is what that is about. But it's possible. So to use some other clever method to find it. All right. Yep. So that was that about deep learning. So do you have any questions so far? Then okay, so then I will go on to reinforcement learning, which was also really big. So reinforcement learning, of course, is the when you train something. The idea comes from nature that you have this agent, and when it does something good, you will reward it, and when it does something bad, it will get a punishment. Okay, so one thing that was pretty hot was reinforcement learning with multiple agents, and they used some of the guys used StarCraft, and this was not because you want to make StarCraft better, because usually then you would just have one agent that controls all the units, but there was. It's good to use computer games when you test your ideas, because it is like a good environment to do the testing in. So they were putting like all of these guys were different agents, and then you want to teach them to cooperate. And one would think that cooperation would come naturally. So you just you just give them like a treat every time they kill a unit or something like that, and then they will all gather together and help each other. But there are some pretty nasty scenarios that like actually like yeah they come up every now and then. So this is a famous one from game theory and prisoner's dilemma. And the thing here is that it's always better to deflect, to confess and say and like give up your partner, even though like even if your partner wants to cooperate with you, it's always better to confess. So it's very hard to get past that. So how do you get people to cooperate if like even if the other guy wants to cooperate, it's better not to cooperate with him, and then he loses, so he don't want to cooperate with you then. Okay, so this is a problem, and so there's actually like yeah, there are some real world things that comes up. For example, like the when people fish out all the fish in the sea and stuff like that would be a real example of prisoner's dilemma. Uh, so evolution have solved it in humans to some degrees by giving us ethics and morals. So you want to have something similar in in your agents when you try to learn. Okay, so that was what they were trying to do. All right. Yeah. Yeah. You have to give them rules beforehand. So yeah, exactly. Be nice to the other guys. And yeah. That's a good one. It's called tit for tat. So it's a very good strategy, and humans have that too. So yeah, you want to give them something like that. Okay, so and then there are some other stuff in reinforcement learning that doesn't work very good. So did, did this boat it has learned that it can get a very good short-term reward by taking these points here. And the short-term reward is so big, so it doesn't try to finish the race, which was like the ultimate goal. But the ultimate goal is so far away, so it just do like this all the time. So and yeah, you don't want your self-driving cars to do stuff like this. So how do you fix it? So one thing that people are talking about is imitation learning. So a human is teaching the agent what to do, and the agent just imitate. And there are a couple of different. I will talk about behavioral cloning, which is the simplest one. Um, for example, you can use it when you want to film basketball games or any other sports event. So the human is filming, and then the computer is watching, and it kind of gets the idea. Okay, what is important? Okay, the ball is probably important. Then it has some problem with it overfits a little bit, so it becomes a little bit stuttery. So, but that was pretty easy to solve. They just solved it with regularization, which is like the usual cure for overfitting in linear regressions and stuff like that. So that actually worked pretty good. Imitation learning. Here is also some pretty good imitation learning. Um, yep. Um, so this guy is talking, and then the anime. They did this for Disney Studios, and yeah, I thought this was pretty interesting. I saw some other guy that talked about stuff like this. That yeah, you could animate another human, and it could have some pretty disastrous results. So, for example, like imagine one day on Twitter a video comes up where Donald Trump says he's going to nuke North Korea or something like that, and North Korea they have to respond. So yeah, that's like and then it turns out that it's just a fake of Donald Trump that do like this, and also there are ways today to fake his voice also, and yeah, I think this could become a problem in the future when this technique becomes better. And I think also one of the problem is that it will be so available and so easy. So I'm not telling any of you guys to do this, but yeah, you probably could do it. You know, fake Donald Trump nuking North Korea, saying that he's going to nuke North Korea. So yeah, dangerous technique, but also cool. All right. So behavioral cloning also have some problems. So here is a car, and they were trying to teach it to drive around, and it made a little mistake. So it got to a point where it hadn't seen what the human would do at that point, because the human never was that close to the edge or something like that, and then it had no idea what to do. So it just crashes. So that is one of the problem with behavioral cloning. Um, and then we have some other learning from human preference. So it's similar to imitation the behavioral cloning, but instead you have two agents here. They try to do stuff, and then you just you push a button. Right is better or left is better, and this is a example of online learning where you learn you do and you learn at the same time. But they ran into some problem here because the human that pushed the button, after a while, they kind of got bored of it and stuff like that. Oh, the computer is expecting the human to be this like perfect teacher that knows the ground truth and know what is best. But after a while, if human get bored or yeah, it might be a problem because the AI don't know that. So yeah. So they had some small problems with that. All right, and then you go out in the hallway, and then there is the chess championship. So there's people playing chess, and you think, oh yeah, cool. So perhaps I can try it out, but of course you can't because it's only for computers. And if you tried it out, you would get your ass kicked a lot because chess computers today they utterly destroy every human. So the winner was Komodo. And I won't talk more about Komodo because I don't know very much about it. So instead, I would just say a few words about another chess engine that I know a little bit more about, or two others, and that is Stockfish and AlphaZero. So Stockfish is it's a very strong engine, stronger than any human, almost as strong as Komodo, and it is won a lot of prizes. It uses old-fashioned AI, where you have this tree, the minimax algorithm, which is like, okay, if I do this, he will do that, and then I will do that, and he will do this, and then you go down the tree, and then you can't go all the way because the tree branched too much. So after a while you have to stop, and then some human has to say, okay, so if you have more pieces than the other guy has, it's good. Or this piece is worth 5 and this is worth 1. So heuristics that humans make up. So that is how Stockfish work. AlphaZero, it works a little bit different. It doesn't. It has almost no human input, so it has a little bit of human input, like that. Yeah, well, the chessboard is sort of symmetric and stuff like that, but they don't show it how to win chess. So it just plays itself for several hours, and then it has a value network, and the value network kind of learns uh, what type of pieces are most valuable, and if the board look like this, is this good or bad, and stuff like that. So it get this more intuitive feeling for what is good. So when it played, so here is AlphaZero, and it did some pretty strange things. It moved same piece twice, and that's like a big no-no. But it did. It sacrificed pieces for positions, which is, I think, yeah, a big strength. So if you just look at this, you will see that AlphaZero is down 2 pawns. So it looks like AlphaZero is losing. But actually, if you look up here, this knight, he can't move anywhere. It's totally blocked out, and it blocks the tower. So so this is actually a very bad position for Stockfish, even though it's up 2 pawns. And this is something that Stockfish didn't really notice, but AlphaZero did. So and yeah, this ended in 117 moves because they're both so good. So no one will really fool the other one. You know, you won't make like this really big reveal after a while that, oh, you didn't get this, I was making this trap. But instead they just like go on and go on, and then they're almost the same. But AlphaZero is a little bit better, and it was every time. You know, they had a lot of games, and AlphaZero won, or they made a draw on every game. So AlphaZero might be the strongest engine today. So it didn't play on the chess tournament, but if it did, I think it would beat Komodo. All right. Yeah. 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 Oh, it did. It competed against itself, and that's how it learned. And there's only one implementation. So they want to make a very general algorithm where they don't tell one AlphaZero you should play like this and one AlphaZero to play like that. It basically just says, here are the rules for chess. Just play along, and then after a couple of hours, it has done a couple of million games, and that's. Okay, if they're yeah. So I think that there might be small differences, but it will probably be almost the same strength. But yeah, one might be like a little bit better than the other one. So, but yeah, if you have two AlphaZero play against each other for 3 hours or 4 hours, they will probably be almost equally good. I think so. So I don't know. Okay. All right. All right. Good. Then we can see if it's actually stronger than Komodo. Okay. 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 Very interesting. All right. So moving on. So now I'm going to talk a little bit about fairness in machine learning. See how. Yep. Um, okay. So uh, machine learning is like in a lot of places in society today. So it will have some societal impacts, and the people are starting to notice, and they're starting to think, okay, is this good? Is this bad? What's the moral of the stuff? And recently, it was in the news about Amazon's hiring engine that it was. Amazon were trying to automate their hiring process with machine learning, but the machine started to sort out things like women's college and stuff like that. So obviously that is a problem. And so from what I heard about the Amazon engine, it was usually a case of GIGO, garbage in, garbage out. So Amazon has like hired mostly guys, and then of course if you train the algorithm on those, it will say, okay, so guys is obviously better, so we don't have anyone working here from a women's college, so I'm going to sort out that. So the solution might be to like train on a better training set or something like that, and be aware about of this. But there are also other problems. So here's another problem from United States. So a lot of banks, I think also like same thing in Sweden, but United States, a lot of banks use machine learning to figure out who are they going to give loans to. And this is another type of problem, because there are some people that won't be able to, so will have a lower chance of be able to pay back because they're part of a disadvantaged group. So, for example, like if you have poor parents or something like that, they won't bail you out if you won't be able to pay back. So the solution here is that you perhaps say, okay, so having poor parents is a protected group then. So the bank has to loan the same percentage to this protected group as to any other group. But that might also pose a problem, because then some of the guys in a protected group, they won't be able to pay back. And then the next year, the group as a whole will have worse credit score. So then there were they were investigating different strategies. So demographic parity, which is like you say, okay, so same percentage, or equal opportunity, which is another way, and you try to figure out which which is which is the best balance to achieve most fairness. So that was they were doing there. Okay, so now we're going to talk a little bit about future. Okay, so there was someone talking about AI safety, and it's pretty interesting, I think, because the people working with AI safety, they have a very different view of what the problem is from like the person on the street, or film directors and people like that. Because usually, like science fiction authors and film directors, they usually think that AI will gain consciousness, and then they will like attack us and try to kill us all. But people working with AI safety, they have another idea, and I think it was pretty nicely illustrated with this example. So here's an example that the AI researchers, they were trying to optimize this robot, and they told it, okay, so you shouldn't. You shouldn't touch the floor with your feet very much, because it's perhaps it's a way of saving fuel or something like that. So how little can you touch the floor? And then they got back the results, and it says, okay, so I can solve it with 0% of the time I touch the floor. Okay, so they were quite amazed. So, and how did it do it? Well, it did like this. Okay, so it turns around, and this was totally unexpected. So and it did. So stuff like this might become a problem in the future, where we have like a very intelligent AI and we give it we give it a task, but we don't really. It can have some unexpected consequences that are bad for us. So easy. Yeah. This is something that we need to have in the back of our heads when we're dealing with intelligent AI. Okay, and then of course people are talking a little bit about artificial general intelligence. So this is what one would call human-like intelligence. So we're not there yet, but of course this is like the dream of everyone at ICML that you want to get here. So what can't we do today? So one thing is that the general artificial general intelligence, we wanted to use a small training set. Because today we have to to recognize a cat, we have to have like millions of images of cats, and obviously that's not how human works. You know, you can see a child can see a cat 2 times and then it knows. And also it's a problem with self-driving cars, because we don't want to crash the car thousands of times before we actually get like a good self-driving car intelligence. So and then people can like do it in 20 hours or so of like training, and don't crash the car at all, and then they know how to drive it. So that is something that we want to. Logical reasoning is also a problem with AI. They can't really count or stuff like that. Or at least like the machine learning AI. So like the good old-fashioned AI, it can do logical research, logical reasoning, but you would want like a deep learning neural network to be able to count, because today, like for example, like every human here, if I just say a number like 1,500,033 or something like that, every one of you like have a feeling, and you know that number, and you know what's come before and after, and then if it's divisible and stuff like that. But AI, if it has never seen that number, so I obviously, or probably is, none of you guys have ever encountered that number that I just say before, but you can still make some, like draw some conclusions about it, but neural network can't do that. So that is a problem. Common sense, also a very big problem, you know, like yeah, it lacks it. Causal reasoning also, like if I do something, what will that lead to? Okay, so Geoff Hinton and Jan LeCun, so some of the legends in neural networks, they discussed this a little bit. So Geoff Hinton, he has this idea that we can't have supervised learning is not what humans do a lot. You know, we do a little bit in school, but we have so many neurons in our brains, so we would have to like learn 100,000 of things every second to be able to fill our brains the way we do. And obviously you can't do that in school. You know, you can't teach people 100,000 things every second. So where does all this information come from? So Jan LeCun, he has this idea that it might be self-supervised learning. So you try to predict the future from the past, or perhaps you like just put the hand on your eye like this, and you try to predict, okay, what is there. So you do this all the time as a human. You know, you walk around in the world and you constantly try to predict what is happening. So what will happen next, and then if it happens like this, okay, you say, okay, it's good, and if something else happens, you correct it. So this is a way to learn about the world, that you don't need a teacher or any labeled sets and stuff like that. You can just use the world as it is. So I thought that was a pretty interesting idea. Okay, and then we have this one, machine reasoning. DeepMind, they have a new neural network that they called a wild relational network that can do IQ test. So these are the Raven matrices, and it's like you use it to test spatial reasoning in humans. So yeah, just like by show of hand, how many think this is A should be the one here. Okay, yeah. Okay, how many think is B? C? Never mind. I won't test you. Okay, so the one here is A because it's just counting. Okay, so 2, 3, 4, and then 3, 4, 5, and then 2, 3, and then it should be 4 over there. So the AI, like most deep learning today, is super bad at this. Okay, but DeepMind's the wild relational net, it's only bad. It's not super bad. Okay, so they could get it to understand some of this stuff, but then they changed it into colors and shapes, and it didn't work. So yeah, this is an interesting frontier. You know, we would like it to be able to do like this. Okay, and then some other people, they have this idea that we should learn a neural network like a child. Okay, and this is a very old idea. So Turing wrote this paper, and he also has this idea that we should have we should teach the neural network like a small child, and then it grows up and it becomes more and more intelligent, like we do humans. But it's harder than one might think. So here are some people that are trying this like interactive task learning, where you interact with this robot and you try to teach it how to make a smoothie. And it turns out that it's a very, very hard problem because you don't have a common ground. So this is the algorithm to make a smoothie. So take the strawberries from the box, slice them into pieces, and add them to the blender. So the humans that try to teach the AI to do this say like this, and they think, okay, so yeah, probably this would teach the AI. But then the AI, it doesn't understand that the strawberries has to be put somewhere first. Okay, so like a cutting board, and you need some tools like a knife for slicing, and you have to put the lid on the blender and stuff like that. So the AI don't understand this stuff, and it's very hard for human to teach an AI because we're always like assuming that, of course, when you're cutting something, you need to put it on a cutting board. So humans are pretty bad teachers for an AI that lacks this type of common sense. So what we're trying, their idea was that, okay, perhaps if we teach it some causal reasoning, it will have more common sense. So they were teaching it, okay, so if you peel an orange, it looks different from before you peeled it. So this is not obvious to an AI. So they were teaching it a lot of stuff like that. So what happens if I cut a cucumber? It looks different after I cut it. Yeah, they had some success with it, but yeah, the robot was still very stupid. All right. So in conclusion, deep learning is still going strong, and GANs are very popular. Reinforcement learning is popular also, and imitation learning was something a lot of people talked about. People are worried about the societal impact of machine learning since it's so common today. And then there are some problems that need to be solved, like we need so much training data, and the machines can't reason abstractly very good, and we lack common sense, and they lack common sense, and so most of this stuff, it looked like pretty bleak, you know, like they weren't really able to like the IQ test robot, it wasn't very good, and the robot making smoothie, it didn't work very well, but they made like small incremental steps, and it's like even though they're very small steps, I thought it was very impressive. I don't know, it's like it's so cool because like we make small steps, and like after a while we will get there. We will get artificial general intelligence, like human level or perhaps superhuman level intelligence, and when we get there, that will change everything, you know. It will be like the biggest thing that ever happened to humanity. So even these like small steps are yeah, they're pretty cool, even though they're so small. Okay, yeah, that's everything. Thank you.